So in working with Newton's second law, net force equals ma. And as it says up here, we're now going to be, mathematically solving problems that could require one or more of a large selections of equations. So acceleration links to all of those concepts we did from kinematics. That very first test we did, initial velocity, position, initial position, final position, time, all of that stuff we did before can be used and incorporated in a problem to try and figure out acceleration. All the stuff we just did on the test that you got back, that stuff all can work with net force. So this equation puts those two together. So the types of questions that you could be asked or problems to solve are near infinite. There's so many mathematical choices I have to create problems. So more practice is definitely the best situation. So in your handbook, we're now looking in one problem, you're going to be looking up at your motion equations, right? That first row, and your force equations down here. So one problem could use a few of these. They might have to use an acceleration formula, right? Or a position formula in order to calculate acceleration. Like there's a wide variety of things that we can do. Now the only formula we haven't used yet is this second one with the summation signs. We'll be getting that again after next week's computer lab week. Week after that, we'll be getting to this one. It just deals with a situation where you might have more than one mass, like a pulley system. All right, so let's back to that note page. So the net force involves problems that we just did, where there's no velocity or time or position data given. Right? The other side of it is your kinematic stuff. We're putting those together. And the bottom part of this, you don't have to write down, but it's just a reminder to you, because a lot of people like to panic at this section because it's wide open into what equation do I have to use. That tends to be the first question I get. Just tell me the equation to use. That doesn't help you. If I just tell you what to do, it's not going to help you in the long run. So it's all about problem solving, reading the question, picking out the information that's given, look at where you need to go, what needs to be calculated, and figuring out how to get there. And sometimes you just look at what's given and realize, you know what, with the information given, I can calculate force of friction, so I'm just going to go ahead and do that. Or with the information given, I can calculate acceleration. I don't know if I need it yet. I'm just going to go ahead and do that. And sometimes that's the approach you take. Right? And then it leads to realizing, oh, that's the right thing to do or the wrong thing to do. Right? So be patient with yourself a little bit. Give yourself a chance to practice the equations, okay, and practice this stuff. But that's the key thing. If you're not practicing it and looking at maybe the online videos or the notes off the internet or asking for extra help from me or from someone else, then you may really struggle. Okay? So definitely make sure you keep up with practicing it. All right. And just a little important difference here, like you may in math class, here's an equation, solve it. We have to figure out which equation to use. And that is a very big difference. That is a different level and way of thinking, right? To figure out what equation to use, or in the case of net force, to make your own equation. Like that's another level higher than just trying to pick the right one, right? Because most often the question you're asked to solve for isn't the first equation to use. So for example, you don't write this down yet, but here's a question, and part two is calculate the acceleration. I could ask you to calculate the acceleration without asking you to calculate the net force in question one, but you should be able to know that you need to calculate the net force in order to figure out what the acceleration is. Okay? So that's, again, part of the problem solving. All right, so please take a moment and jot this down, and we'll go through it. So the first problem we're looking at that's combining dynamics, why an object is moving, and kinematics, analyzing how it is moving. Okay? And now you have to be careful with questions like this. If we get question one wrong, like if we don't have the answers with us and you make a mistake with question one, you're going to get question two wrong, most likely. So you can still get credit and a decent amount of marks and evaluation for the second question, but it's still going to be incorrect. And then any subsequent questions are still incorrect. So you would never have this question on a test. It's just too much of a risk that you're going to get, parts 3 and 4 incorrect if questions 1 and 2 don't go right. All right, so let's see what we can do here in about 10 minutes to get this question done. We've got an applied force 50 newtons. Okay, so just think of it as someone's pushing with 50 newtons of force. So that's like lifting 5 kilograms, roughly 13 pounds, just lifting up 13 pounds. I'm trying to picture what that force feels like. It's used to accelerate an object across a frictional surface. So there's a friction existing between this object we're pushing and the surface. The friction, so the object encounters 10 newtons of frictional force, and the mass of the object is 8 kilograms. So the mass doesn't come in until we need to use Newton's second law, F equals ma. Right? Here we're going to calculate the net force. Because friction is given for us, that saves us some steps. And on the test you just did, friction might not have been given, and you would have had to use the friction formula and all that. We don't need to do all those steps for this problem. So one, we're calculating the net force. So that's our goal, first of all. So now we have two equations for net force. It's the sum of all the forces, or we can apply Newton's second law, F equals ma. Now, if you read the question, there's no acceleration given. There is no velocity information given. There's no time information given. There's no position information given. So using the kinematic equations to solve for acceleration doesn't make any sense right now. So we can't solve net force with Newton's second law. We're going to have to use the definition, which is the sum, the vector sum of all the forces. Let's keep writing what we have. We have applied force of 50. Force applied equals 50 newtons. We're given that the force of friction, now in the way the problem's worded, you're given the magnitude of the force of friction, right? It encounters 10 newtons of frictional force. In terms of direction, now it's set up here in the problem, right, positive, left, negative. Let's say this object's moving to the right. Does friction positive or negative? Negative. So it's going to be negative 10 down here. Really important. Otherwise, your net force becomes 60 instead of 40. And we have our mass, which is 8, but we don't need that. I'm not going to write it down. So net force is, not FET, F net. So the sum of all the forces. Now, it's not every single force in the problem. It's only the forces that are acting the way this thing is being pushed horizontally. We're not worrying about gravity or normal force. We can't add them all together. They're independent of each other. Net force is going to be force applied plus force of friction. Kind of what we went through last Friday on your test and preparing for it. So net force equals the applied force of 50 added to the force of friction, which is negative 10. So there was a couple of instances on your test where you forgot to put that friction in as negative. Right? The direction matters for that net force formula. Net force is 40. 40 newtons of net force. Okay, so once you overcome friction. Second question, acceleration. Well, now we have net force. Now we have the mass as well. We can go straight to Newton's second law. So 40 equals 8 times the acceleration. So divide both sides by 8. So it's 5.
The boys soccer team are reminded to get their uniforms at the beginning of lunch for the team pitcher. So if you were on the boys soccer team, you got your uniform for the pitcher at the beginning of lunch.
I don't know why the answer in brackets with this question is 4.9. Maybe it's a remnant of an old question I used to do, but it's very close. But it should be 5. I mean, 40 divided by 8 is 5. Not quite sure what's going on there. Questions for the first two. That's the main part of what we're the kind of questions we're going to be experiencing. So in other questions, you might have to do Newton's first law first, and then something else, or maybe instead of solving for net force first, you solve for acceleration first. So really quickly, let's do question 3. We'll get this done in a couple minutes. And we'll pick up with question 4 later on. Reread the question here in a second. But it's asking you in kind of a long way, after that initial push, how far is it going to go if we can keep a applying the same force, so you maintain the same acceleration for 12 seconds. Where does it end up from the starting point after 12 seconds? So this is straight up kinematics problem. So if you had the acceleration incorrect, again, if you're doing everything correctly for solving for final position, you're still going to get credit for doing that. So I have my acceleration now, 5.0, it's positive. What's initial position? Do you remember what happens if it's not really given? Initial position is 0. Initial velocity. Remember, we're talking about this object is moving and how far it's going to go. Well, initially it was not moving at all. Right? You're just getting it moving. So as soon as it starts to move, initial position 0, and time 12 seconds. It's easy to forget about those zeros, and it's really important to solve the problem. Otherwise, we don't have an equation, a relationship that's going to work. So when you look through your handbook for an equation, right, start looking through, well, I'm trying to solve for final position. I've got two equations with final position with it. This one, it's already solved for final position, involves initial position, initial velocity, and acceleration and time, lots of other variables. And this one over here has final position in it, and maybe less variables to work with, but the equation we're looking at here does not have has final velocity in it. We do not have final velocity, right? So that's not going to work well for us. So what we are going to do is use this one, right? Final position is the initial plus the initial velocity multiplied by the time plus half at squared. That equation becomes quite a bit simplified when we start putting in these variables that are 0. So I'll write it out. Initial position plus final initial velocity t plus 1/2 at squared. So that final position is 0 plus 0t plus 1/2. Oh, t is 12, sorry. Put my numbers in. A is 5, t is 12. Please don't forget that 0 multiplied by anything is 0. If you do this question too quickly, I've seen it happen already where people write down 12. It's not 1 times 12, it's 0 times 12. And that's just a little thing maybe from going too fast. So all you end up doing is half of 5, which is 2.5. 12 squared is 144. Multiply the two of them together, and it's around 343 meters. So if you want to keep moving for 12 seconds, you need 343 meters of distance in front of you to keep applying this force. Now the second part 4 will be interesting too, but we'll do that another day. We're going to run out of time here. But we'll do that question next week if we get a chance during the computer lab stuff or the week after that.